Good evening, ma'am.
Good evening. Hi Riyasat. Every time how you join this meeting, you go to that Gate NPTEL portal and then you join, right?
Okay, okay.
No, I am asking how you are attending this meeting. Like from where are you getting the link?
Gate M Gate MTPL.
Gate NPTEL portal, no?
हाँ.
Okay.
Yes, ma'am. Portal से.
Okay. Actually, like the topic and all that is not mentioned for my
Yes,
course
ma'am.
for
Yes,
last
ma'am.
two classes. I feel that's why the attendance is this low. I don't know why they have not updated. So I
Yes, मैम.
inform
अभी
them.
मैंने चेक किया तो वो भी वहाँ पे.
हाँ
यस
अभी
मैम.
तुमने चेक किया तो
अपडेट. हाँ, तो उस पे मेंशन नहीं था तो मुझे लगा क्लास नहीं चलेगी, लेकिन फिर मैंने रैंडमली सोचा कि लॉ ज्वाइन करते हैं, तो फिर मैं ज्वाइन हो गई.
हाँ वही मुझे भी लग रहा है लास्ट दिन भी नहीं था तो इसलिए अटेंडेंस कम था उस दिन भी
यस.
सो यू वर देयर इन द लास्ट क्लास में थे तुम
यस मैम. यस मैम. यस मैम.
ओके सो हम उसी से स्टार्ट करते हैं फिर जो ज्वाइन करेगा करते रहेंगे 7-6 हो रहा है
ओके.
ऑलरेडी ओके स्टार्ट स्क्रीन विजिबल है
यस मैम.
सो लास्ट क्लास में एक्चुअली द लास्ट क्वेश्चन विच वी सॉल्व was this. So there was some confusion with this question. So I would like to like go over this question. That's why once again. Okay. So here the question was like this question is from GATE 2020 chemistry. Question number 48. The question is among the following B12H12 whole 2 minus nickel whole 5 CO whole 12 2 minus C2B9 H11 whole 2 minus rhodium 6 CO whole 16 OS6 CO whole 20 B5H11 and B6H10 the total number of species having nido structure is fill in the blanks. Okay, so this is the question. So here we have to write that how many of them are having nido structure. So for that we will use the weights rule. Okay, so as per the weights rule, if we are having B and HN type of compounds, B and HN and here let's say N or X minus. So for this type of compounds, we can generalize as if it is BnHn whole 2 minus, then the structure is closo. If it is BnHn whole 4 minus, then it is nido. If it is BnHn 6 minus, then the structure is arachno. Okay. So from this, how many like structure of how many compounds we can know about this. This is B12H12 2 minus, right? So this one we can write as BnHn 2 minus. So what is the structure of this?
Clozo.
Yeah. So it is closer. Now, moving on to the next, this compound which consists of only this boron and hydrogen. This is B5H11, right? So B5H11, how we can write? B5H5 and then 6 minus. Why 6 minus? Because 5 plus 6 is
हाँ.
11. So H we can write as H5 and then 6 minus charge. Okay. So then this has what structure?
Arachno.
Yeah. So this has arachno structure. Now moving on to the next complex, which is B6H10. B6H10 means B6H6 and then
4
4 minus,
4
right?
minus.
Yeah. So it has a nido structure, right? Then moving on to this, which is C2B9H11 2 minus. Now carbon is isolable to one boron and one hydrogen, right? So as it is isolable to one boron and one hydrogen, we can write BH2, then B9H11 and 2 minus, right? So that means B11H13 2 minus, which is equivalent to B11H11 4 minus. So what is the structure of this complex?
Nido.
Yeah. Now moving on to the metal complexes. Okay, so for metal carbonyl complexes, last time the confusion was that like I mistakenly told you you people the incorrect formula. So the formula should be actually uh, like skeleton total skeletal electron pairs. We have to find out, and for finding out this, the formula is total number of valence electrons minus 12 into n, where n is what? N is the number of, it is hanging, just wait a second. 12 into n, where n is the number of metals. Okay. And here is total number of metals. Fine. Divided this whole thing divided by 2. This whole divided by 2. Okay. Now, uh, for these type of complexes, like for metal carbonyl, these are metal carbonyls, right? So for metal carbonyl complexes, this weight rule, as per weight rule, it will be if the skeleton electron pair is equal to n plus 1, where this n is again the total number of metals. If it is n plus 1, then the structure is closo. If it is n plus 2, then the structure is nido. And if it is n plus 3, then the structure is arachno. Okay. So now for this complex Ni5CO12, Ni5CO12 whole 2 minus. Okay. So tell me what is the total number of valence electrons in this complex? Hello? Nickel is having how many electrons?
10 ma'am, 3d8 4s2.
Yeah. So it will be 5 into 10 plus carbonyl gives how many electrons?
24 ma'am.
Okay. So it will be then 5 into 5, this thing is not responding. 5 into 10 plus 12 into 2, which is equal to your 20 plus 24, right? Then this will be equal to plus 2, okay, because it has a total charge of minus 2. That means it is having 50 plus 24 plus 2, which is equal to, okay, so 76, right? So it is having, I'm writing it here, 76. 76 is the total valence electrons. Now, this minus 12 into n. There are how many metals in this complex? 5, right? So, it is equal to 60 divided by 2. So, 76 minus 60 divided by 2, which is equal to 16 by 2, which is 8. And there are 5 5 number of metal centers. Then it is 5 plus 3, which is 8. So the structure is arachno here, right? Now moving on to the next metal complex, which is rhodium 6 and CO whole 6. Now rhodium is in which group? Cobalt, rhodium, iridium, right? So it is having 9 electrons. So for this rhodium complex, it will have 6 into 9 plus 16 into 2, right? Total valence electrons is 6 into 9, which is 54, plus 16 into 2 is 32. That is 86. Okay. So it will be 86, and then minus 12n. 12n means here n, the value of n is 6. So it will be 86 minus 12 into 6, which is 14, right? So it will be 14, and then total number of skeleton electron pair means this 14 divided by 2, which is equal to 7. Fine, 7, and here how many number of metal centers were there? 6. So here n plus 1, right? So the structure is,
Clozo.
yeah. So here the structure will be closer. Now the last complex, which is this osmium complex, having OS6. There is some problem with my pen. Okay. So we are having osmium 6. Now osmium is in which group? Iron, ruthenium, osmium, right? So it is giving 8 electrons. Then 6 into 8, okay, plus carbonyl is giving 2 each, 20 into 2. Fine. So it is 6 each 48 plus 40. Fine. So this is equal to 88. And minus 12 into n means 12 into how many metal centers? 6, right? So it will be 88 minus 12 into 6, correct? 12 into 6, which is equal to 16 again, and 16. Then number of skeleton electron pairs will be skeleton electrons by 2, which is equal to 8. So here n plus 2, n plus 2 means what is the structure?
Nido, ma'am.
Nido.
Nido, right? So therefore, in this question, there are total how many structures which are having nido? How many complexes having nido structure? One was this complex, okay, osmium, which we found out right now. One is this B6H10 complex, and the other one is this C2B9H11 2 minus, right? So here the answer to this question will be the total number of species having nido structure is 3. Is it clear?
Yes, ma'am.
Yeah. So last day, whoever told that it is the other way around. Thank you. I also missed that. Okay. Yeah. Now we will move on to the next question. So 2020, almost inorganic questions are over. If you have doubt in any other inorganic chemistry question, you can ask me like ask me that whenever you want. And so now we will be moving on to 2019 paper. Okay. So 2019 paper, first we will discuss about this question. The first inorganic chemistry question which came in 2019 gate paper is this. The question is the incorrect statement about the interhalogen compound ICl3 is it exists as a dimer. Geometry around the iodine is tetrahedral in solid state. It decomposes as ICl and Cl2 in gas phase. And the last option is liquid ICl3 conducts electricity. So these are the options given for this question. So this question is from main group chemistry. These type of compounds which are given here, this ICl3, we call these compounds interhalogen compounds. Okay. So interhalogen compounds means in that compound only halogens will be present. Interhalogen compounds are made mostly like they are synthesized by reacting to different type of halogens. So here they are asking about ICl3. Okay, that is iodine trichloride. So the first option given here is it exists as dimer. Okay, so ICl3, this ICl3 is actually like present as it can't stay like this. So the form which is it will always form dimer. So the first statement is true, and like it will be present like this. Here we will have two Cl which will be like terminally coordinated, and there will be one chlorine which will be which will have this coordinate bond, and it is bridging chlorine. And similarly here another I will be there. This is bridging and two terminal Cl. So this iodine chloride, this complex exists as a diamond. So the first statement is true. Okay. Then the next option given, so this is true. Okay, it exists as a dimer. Then the next option is option number B. Geometry around the iodine is tetrahedral in solid state. So now here in solid state it exists like a dimer. Okay. So anybody, can you tell me what will be the structure of this like geometry of this compound if it is present as ICl3?
Trigonal bipyramidal.
Yeah. So it will be trigonal bipyramidal as iodine is having three bond pairs with Cl and there are two lone pairs present, right? So the structure is TBP, that is trigonal bipyramidal. If it was present as ICl3, then the geometry would have been trigonal bipyramidal. And if they ask you the shape, since there are two lone pairs and three bond pairs only, the structure would have been like this. Okay, Cl, 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 and then two lone pairs. Okay, so the structure is T-shaped. But since ICl3 does not belong like this, it will always like it will be present in dimer form. Therefore, here you can see that they are present in a plane. Okay, so in this case, the structure of this is square planar. Okay, but you people should know that for other complexes, other interhalogen compounds, for example, ClF3 and all, they have this TBP geometry and T shape. Okay, but since this is a dimer, here this iodine is making like it is present like this with four bonds. You can see this. So and it is a completely planar molecule. So here the structure is of the central atom. This is square planar. Okay. So that means we can see that this option is nowhere correct. Even if it is present as ICl3, it will have a it will have a square trigonal bi bipyramidal geometry. And since it is not present as ICl3, this if they are asking about I2Cl6, then it is having a square planar structure, and this ICl3 will have a trigonal bipyramidal geometry. Now the next option, so we know that this option is incorrect, right? That we understood. But let's discuss about the other options as well. The next option given is option number C. It decomposes as ICl and Cl2 in gas phase. So this statement is also true that when it is, sorry, this is not liquid. This is gaseous. I2CL6. Okay, gaseous ICl3. Hmm. So actually, in gas form, it can be present like this ICl3. Okay, but if we go to liquid or solid form, it is present as a dimer. But in this, if it is present as ICl3, it can like decompose into ICl and Cl2. We know that Cl2 is like very stable. It is chlorine gas, and ICl is also stable as compared to ICl3. So this ICl3 in gaseous phase decomposes into iodine monochloride and chlorine gas. Okay, and the next option which is given, so this statement is also true. Now moving on to the last option, which is option number D, liquid ICl3 conducts electricity. In liquid phase also, as I said, that in liquid phase also, this will ICl3 will remain as its dimer only, I2Cl6. And what happens is it can ionize, like self ionize into ICl2 plus and ICl4 minus. So this is self ionizing. Okay. Because of this ionization, it can like cation and anion both are present. So this is like this can conduct electricity. So it is a moderate conductor of electricity. That means this option is also correct. Conducts. Okay. So moving on to the question again, that so this is also true, right? So the incorrect statement about the interhalogen compounds ICl3 is the option number A is correct. It exists as dimer. Option number B, that is geometry around the iodine is tetrahedral in solid state, is wrong. Option number C, it decomposes as ICl and Cl2 in gas phase. This is true. Option number G, liquid ICl3 conducts electricity. This is also true. So the answer for this question will be geometry around the iodine is tetrahedral in solid state. Is it clear? Is it clear?
Yes, ma'am.
Okay. So, in NPTEL, like in that GATE NPTEL website only, you can find various like lecture series by different professors. So there is a lecture series by Professor MS Balakrishna. You can follow the his videos from main group chemistry for better understanding of the topic. Okay. So next we will move on to the next inorganic question which came in GATE 2019 paper. So the question is, the incorrect statement about silicone is. Okay, so what is the incorrect statement about silicone? The options given are option number A, they are thermally unstable because of the silicon carbon bond. Option number B, they are insoluble in water. Option number C, they are organosilicon polymers. Option number D, they have stable silica-like skeleton. This is silica-like skeleton. Okay, SiO, SiO, like this. So here in this question, they are asking us about silicones. So this is again a question from main group chemistry, and this is on group 14 elements. Okay. So first of all, what is silicone? So F.S. Kipping was the person who discovered the silicones. He was carrying out the reaction between this alkyl and aryl substituted chlorosilane. Okay, like here these R groups are can be either alkyl or aryl. So when he reacted this with water, he observed that these two chlorine got replaced by two hydroxide groups, and then further removal of H2O gave this compound silicone. Okay, here you can see if we take two molecules of this alkyl or aryl substituted this chlorosilicones, when they like the reaction of them with water will give this, and if you take two molecules of this, then they will react, this H2O will release. Okay, H2O will release and this will form, and these are called silicones. Okay, so this chain can go on. Like if we take more number of if we have another, let's say we have another molecule of this Si, R, R, OH and OH, then what will happen? Again one molecule of water will get eliminated, and we will get OH, Si, R, R, O, Si, R, R, right? Right. So like this chain can go on. So basically, this again hanging. These are silicones. Okay. So here we can see like what were the options given, that uh, they are thermally unstable because of silicon carbon bond. They are insoluble in water, they are organosilicon polymers, and they have stable silica-like skeleton. So let's go with this option first. They are, here we can see that what are organometallic compounds? Anyone? By organometallic compounds, we mean like if we give a generalized statement, we can say that there is a metal and there is a metal carbon bond. So because of this carbon, this is the organic moiety and this is the metal. So that's why this is called organometallic compounds. Similarly, here we can see that this R, that means which is alkyl or aryl group, and there is this silicon, so there is a bond between these two. That's why we can call this organosilicon compounds, right? So silicons are organosilicon compounds. Now, as I said, that if we keep on taking more and more number of SiR2 OH whole 2 molecules, this chain can grow infinitely long, right? So that means these are polymers, right? So there was one option which is they are organosilicon polymers. That means these option is correct. Now, moving on to the next one. Uh, They are thermally stable. Silicones are thermally stable compounds. Okay. And from where this stability arises? The stability of silicones are due to the presence of their stable silica-like skeleton. Okay. So, silica-like skeleton means this, right? SiO, like this, it will go on. So, it is having here, we can see this silica-like skeleton. So because of the presence of this, they are thermally stable. And another factor because of which they are stable is that the bond energy, like the bond strength of this SiR means the silicon carbon, this bond, this bond energy is also high. That means these bond is also having high strength. So these two parameters gives rise to the thermal stability of silicon. Okay. So there was one this option as well, that they are here, the option was that they have stable silica-like skeleton. That means this is also true. We saw that in the structure. Now here what in option number A, what they gave is that they are thermally unstable because of SiC bond. But this is not the case, right? One of the reason for their thermal stability is also because of the high bond strength of silicon carbon bonds. So they are silicon carbon bonds are not like they are having high bond strength, so they are the reason for its thermal stability and not thermal instability. So this option which is given, that is option number A, this is incorrect, right? And then this option number B, they are insoluble in water. This option is also correct. Why this is so? Because you can see here, right? See there, the silicones are having this kind of structure. So these are our groups. They are alkyls or aryls. That means they are organic groups. So if we see this molecule from outside, this SiO, this is the skeletal, right? But if we look at it from both the sides, we can see that there are surrounding organic moieties only. Okay, like these are alkyl or aryl groups which are nonpolar in nature, and because of this, silicones are water repulsive and they are not soluble in water. Okay, so coming back to the question, the incorrect statement about the silicons is they are thermally unstable because of SiC bond. No, this option is wrong. They are thermally stable because of SiC and skeletal, this skeletal, silica-like skeleton. They are insoluble in water. Yes, they are insoluble in water. This is because of the presence of the R group, which makes them water repulsive and hence insoluble in water. They are organosilicon polymers. Yes, they are live silicon and carbon bond, and it is polymeric. So they are organosilicon polymers, and they have stable silica-like skeleton, which makes them thermally stable. So the answer for this question number 4 is option number A. They are thermally unstable because of silicon carbon bond. Is it clear?
Yes, ma'am.
So I will make sure that they are updating the page from next week. Because of that, only very few people are joining. Maybe they are thinking that we are not having the classes. We'll do that. Next, moving on to the next question. That is question number 5. Okay. This question is again from GATE 2019, question number 5. So here the question is the delta O value of nickel H2O whole 6 2 plus is 8500 centimeter inverse. The del O values of NiCl6 whole 4 minus and NiNH3 whole 6 2 plus compared to NiH2O whole 6 2 plus are option number A, higher and lower respectively. Option number B, lower and higher respectively. Option number C, higher in both complex ions. Option number D, lower in both complex ions. So if you people remember, if you people are following from the first class only, there is one very similar type of question which was asked in 2021 paper. Okay. So there also they asked about comparing the delta O values and the logic which is to be used for both the questions are same. So first of all, what is this delta O? See, there are total how many d orbitals? 5, right? So the average energy of of the 5d orbitals with ligands, if it is present in spherical crystal fields, then all the d orbitals, all the 5d orbitals are degenerate in energy. But if they are present in an octahedral crystal field, why we are talking of octahedral crystal field here? Because here all the complexes here you can see that all are having 6 ligands coordinated to it, and all the 3 nickel complexes, they are octahedral complexes. So when this metal is present in an octahedral crystal field, the 5 degenerate sets of d orbitals will split into 2 sets. So one set is T2g and the other set is Eg. So in T2g set, the orbitals will be dxy, dxz and dyz. These orbitals are having pi, these are pi type orbitals. They have pi type of character, and in Eg orbital, it will be in Eg set, there are two d orbitals which are dx square minus y square and dz square. Okay. They are sigma type. So now the energy difference between these two sets, that is the T2G and the EG sets, is delta O. Okay. It is the crystal field splitting. Now this value, this delta O, this depends on 3 factors mainly, which are: one is metal charge, the second one is principal quantum number, and the third factor is ligand field strength. Okay. So first of all, checking the charge on the metals. Okay. So here, let's come to this. The 3 complexes which are given are NiH2O whole 6 2 plus, NiCl6 4 minus, NiNH3 whole 6 2 plus. So what is the oxidation of nickel in these complexes? If nickel is having an oxidation state of 6, water gives carries how much charge?
0.
Okay. And the total charge of this complex is 2. Then x plus 0 is 2 and x is plus 2. So for this complex, nickel is present in plus 2 oxidation state. Now moving on to this complex, if X is the oxidation state of nickel, how much charge does chlorine carries?
-1.
Okay, so it is equal to -4. That means X minus 6 is equal to -4 and X is equal to plus 2. Right. So here also nickel is in plus 2 oxidation state. Moving on to the next complex, which is nickel NH3 whole 6 2 plus. Here, if X is the oxidation state of nickel and ammonia carries how much charge?
Zero.
Yeah. So it is also a neutral donor and it carries a charge of 0 and the complex is having a total charge of plus 2. So x plus 0 is plus 2 and x is equal to plus 2. So in this case also nickel is present in plus 2 oxidation state. So we have seen that for all the three complexes the charge on the metal complex are same. So we can't compare on the basis of this, right? This is same. Now the next factor on which it depends is the principal quantum number. For 5D, always the delta O value will be greater than 4D and 3D. So the order is 5D is greater than 4D, which is greater than 3D. But since here the metal is same, that means this factor is also same, and we can't compare these three complexes on the basis of this factor as well. Now, the last factor on which it depends is the ligand field strength. Here we can see that for all the three complexes, the ligands are different. For this case, the ligand is water. For this case, the ligand is this chloride ion. And for this case, the ligand is ammonia, right? So that means we have to compare on the basis of this. Now, as we have already discussed it, but we will again look onto this. This is the spectrochemical series. Okay, so in spectrochemical series, if we move from this left to right in the series, the uh, strength of the ligand is increasing. Okay, so the ligands having the lowest strength are the halides. Okay, these are the halides. We can remember it in this way that the lowest strength, the ligands having lowest strengths are halide, then it is water or this oxygen donating, like if oxygen is the donating group, that type of group will lie somewhere in between. Then comes nitrogen here. So you can just write, we can just write here O, then N, then this P, then CO, Cn minus means all the molecules where C is the donor. From C it is donating to the metal center. Okay. So by this way, you can remember a generalized spectrochemical series. Halides will lie in the lowest, followed by this H2O and all. Then N, in which ammonia will fall. Then phosphine type of ligands. Then CO, CN, these type of pi acceptor compounds. Okay. So now here in what we have seen, the ligands are water, ammonia and Cl minus. So here we can see that Cl minus lies lowest among the three. So Cl minus will be the lowest, then H2O and then NH3. Okay, this is the strength of the ligands. Now if we see that for, like we know, if we are not considering any pi type of interaction and only sigma interaction, which is the case for water type of ligands, then the gap between this T2G and EG is delta O, right? But if the ligand is an halide, then what will happen is halides are electronegative in nature, so they will lie lower in energy in comparison to this metal orbital, and also they have filled pi orbital. Okay, so because of this filled pi orbital and this T2G orbital, both are having pi characters and therefore they will interact with each other to give this bonding set of T2G orbitals and this anti-bonding set of T2G star orbital. Okay, so here we can see that this T2G star is lying closer to this metal T2G orbital, and therefore this anti-bonding T2G star is highly metal-based orbital, So now the T2G has shifted here. This is the new HOMO and this is the LUMO, and the delta O as a result of this interaction has decreased from this value to this value. Okay, so there is decrease of delta O for pi donor type of ligands. Okay, halides are pi donor ligands. And for what happens for pi acceptor ligands? In this case, pi acceptor ligand is not given as an option, but the question which we discussed, which I was talking about, which came in 2021, in that question, CO or CN minus was given. Okay, so if that type of option is given, what happens is, because of the, we know that in CO or CN minus type of ligands, there are empty pi star orbitals, right? Uh, So because of this presence of empty pi star orbital, what happens is, wait, again it went- uh, because of this presence of this empty pi star orbital, here also since it is pi type orbital, this pi will interact with this T2G orbital and it will give rise to one bonding and one anti-bonding orbital, anti-bonding T2G star and bonding T2G. But here in this case, what we can see is this T2G, like this bonding T2G is lying closer in energy with this metal T2G orbital, and as a result of which this is highly metal based. Okay. And EG will remain same since it is having sigma type character, so it will remain same in energy. And from this delta O, which we would have gotten if this is there was only sigma type interaction, we will see that delta O value is increasing because of this pi interaction between this pi acceptor ligands and the metal T2G orbital. So for pi acceptor type of ligands, the delta O value increases. Okay. Now, as because from this petrochemical series, we know that for strong field ligand, the delta O values are increasing. Okay, so that means the highest delta O value will be for the strong field ligand NH3. What happens is strong field ligand, since ammonia is stronger ligand than H2O, it will increase the gap between the like HOMO and LUMO, and therefore it will give the maximum delta O value followed by H2O and the halide complex, and the complex which has halide will give the minimum value. Then coming back to the question, the delta O value of NiH2O whole 6 2 plus is 8500 centimeter inverse. The delta O values for NiCl6 4 minus and NiNH3 whole 6 2 plus compared to this are, so we know now the order NiH2O whole 6 2 plus is lesser than NiNH3 whole 6 2 plus and is greater than NiCl6 whole 4 minus. So NiCl6 4 minus is lower, right? So which are the options there are lower? These two, we can cancel out these two. And then NiNH3 is higher. So lower and higher respectively. This will be the answer, right? Is it clear?
Yes, ma'am.
So there is this coordination chemistry series by Professor Devashish Rai from Department of Chemistry. You can go on and watch his lecture series on coordination chemistry. That will be helpful. So this was clear for everyone.
Yes, ma'am.
Yes, ma'am.
We will move on to the next question then.
मैम ये इस क्वेश्चन को अगर हमें स्पेक्ट्रोकेमिकल सीरीज लर्न हो तो उसके बेसिस पे भी तो कर सकते हैं ऑर्डर के अकॉर्डिंग आंसर तो
हाँ,
वही आएगा
हाँ, एकदम। मतलब मैंने ये भी बोला आप लोगों को कि रीजन क्या है स्पेक्ट्रोकेमिकल सीरीज ऐसे
यस
होने
मैम।
का।
यस मैम।
ओके। ये मतलब स्पेक्ट्रोकेमिकल सीरीज अगर याद रहे तो हाँ तुम्हें, और याद करने के लिए ये सिंपल वे है, ये लोग ज्यादा पास पास कुछ वैसे नहीं देंगे। तो अगर तुम्हें ऐसे याद है कि हेलाइट एक ऑप्शन है, तो हेलाइट के लिए वो सबसे लो ही होंगे। H2O will lie somewhere in between, and अगर कोई पाई एक्सेप्टर टाइप लिगेंड है या हाइड्राइड लिगेंड है या R माइनस टाइप का लिगेंड है, वो स्ट्रॉन्ग फील्ड लिगेंड्स होते हैं। ओके, सो उनके लिए हमेशा डेल्टा O वैल्यू ज्यादा होगा। ओके।
ओके।
Now we will look this question. So this is question number 3 from 2019 paper. So question number 3 is, among the following carbon electrodes, the one with discrete molecular structure is option number A diamond, option number B alpha graphite, option number C beta graphite, sorry, option number D fullerene. So we know that there are various electrodes of carbon. Okay. So, in this question, they are asking that which among the following given electrons have a discrete molecular structure. So, by discrete, they are saying like it is not an array. Okay. So now, if we move on to the structure of graphite. Okay, so graphite has this type of layered structure, and it can go on, right? Like you can see they have given option alpha graphite and beta graphite. So the difference between these two is just that one is having ABA type of packing, and the other one is having ABC type of packing. Okay. So ABC type of packing is, I think it is the hexagonal packing, and ABA type of system, this gives rhombohedral structure. Okay, but in both these cases, you will find this like ABA, it will go on. So it is having an array of structure, like there is no discrete structure for this. So this is an array. So both alpha graphite and beta graphite are having an array, and they don't have a discrete molecular structure. Okay. And then we can see this diamond structure. Here also you can see same patterns like going on. So it is also having an array of structure. Whereas if we see for this fullerene, the most common fullerene which we all know about is Buckminster fullerene, also known as the buckyball, like C60. Here it has a certain number of carbon, right? So it is having a discrete molecular structure. There are other examples of this fullerene like C32 or few more are there. So among the given options, this is the only one which is having a discrete molecular structure, whereas diamond, alpha graphite, beta graphite, all these are having this array. So they are not having discrete molecular structure. Only fullerene is the one which is having discrete structure among the given carbon electrons. Okay, for this, you should have a little bit idea about the structures of these like electrons of carbon. We know that this is important in main group chemistry. Usually, questions from this boron, boron, carbon, silicones, these type of structure, these questions come. So you should know about these carbon electrons. Sometimes they ask about the difference between this diamond and graphite. They can also ask questions like this. Okay, so this is something to remember. If you know the structure, you know the answer. And also for all these main group chemistry questions, the book I am following is JD Lee. Okay, just right. It is JD Lee, Concise Inorganic Chemistry, So there you can find like all these chapters. They have given it kind of crisply, so you can remember that. Well, any questions?
मैम ऑर्गेनोमेटालिक एंड कोऑर्डिनेशन कंपाउंड के लिए बुक बता दीजिए।
Organic organometallics and coordination compound. Mostly, what I follow for coordination compounds, it is RP Sarkar. Okay. Our General and Inorganic Chemistry, Part 2 by R. Sarkar. I will write it in the chat box. Yes. General and Inorganic Chemistry, Part 2. Okay. And for organometallics, you can follow B.D. Gupta. What I say? Main. This J. E. Right? Any questions? I have written the name of the books in the chat box. You people can see. And if you have any questions from 2021, 2020, or this going on 2019 paper, so now we are solving this 2019 questions. You can come up with your questions in the next class. Even if you have any query, you can like if you have any query which is urgent to be solved, you can always mail me in this mail ID.
मैम बायो ऑर्गेनिक केमिस्ट्री।
Uh, Bio inorganic chemistry. So bio inorganic chemistry, I follow it from many books. One among them is by AKD. Okay, Inorganic Chemistry, Volume 2 by AKD. Inorganic Chemistry. But there is one problem with this book. It is that he has described few like things way too much. So don't get scared by that because for GATE, CSIR, all these things, you just want the basic knowledge kind of thing for inorganic chemistry, like for bioinorganic chemistry things. Okay. So you can like just knowing the function of a few common enzymes, like they will not ask you about all the metalloenzymes enzymes. Okay. There will be few common things like which are very common like hemoglobin, myoglobin, superoxide dismutase, cytochrome P450. If you go through various previous year question papers now, you will get to know that there are few metalloenzymes and all only from which they ask most of the time. Okay, so you will get an idea of that. So knowing about that and from like this cytochrome P450 catalase and all, they ask most of the time they give match of the following type of questions where they will ask you the role of that metalloenzyme in body, like what reactions they do and all. Like that, there was one question in 2020 paper also. So these are the type of questions which they mostly give from bioinorganic chemistry. Okay.
ओके थैंक यू मैम।
Yeah. Thanks. Okay, then that's all for today's class. We will meet on next Monday. Okay. Bye.